Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Mousumi Das with us today. Hi, Mousumi.
Hi, how are you this morning? Well, it's evening here.
It is my morning. So this is April 13th, and it's 7 a.m. approximately my time. And so it's 7:30 p.m. in India.
Yes, yes.
So we're doing across the world today. Very cool.
Yeah.
But I'm doing great. Yeah. Let's see. In Phoenix, we are definitely turning into our early summer months. It's getting warmer. And how about India? How are we doing there?
Bangalore is full summer, so it's in the 90s now.
Yes, same here. We're up in the lower 90s right now. So
okay. So we're the same.
We are the same. We're in hot climates.
Yeah.
Oh, very cool. Very cool. And Mousumi, what do you like to do for research?
So I study galaxies, and the focus is galaxy evolution and how galaxy dynamics affects galaxy evolution. That's the broad theme. But I've been doing a lot of things over the years. I do simulations to study galaxies, and I do observations of galaxy interactions, mergers, a lot of things. But it's basically about galaxy evolution.
So you're the proverbial double threat here with both theory and observations.
Yes.
So when do you start building instruments so that you can be all three? Instrument builder?
Yeah, that is the next. Next frontier.
Very good. Cool. And that is going to bring us to this very awesome APJ letter. It's open access, people. You can go get a copy for free. Go grab one. Estimating the Oblateness of dark matter halos using neutral hydrogen velocity dispersion. And Mousumi, take us away.
Okay, thank you so much, Francis. And thank you for this opportunity to share my work. So first of all, before I start, I'd like to thank my collaborators, Roger, who's in Spain, Stacy, who's at Cleveland, Case Western, James Schaumbert, who's also in the US, and Dwarkanath, who's here in Bangalore. So all of them have contributed. Roger has done a lot of the neutral hydrogen velocity dispersion. Stacy has just helped me with building up the problem. James has helped with all the near-infrared data, and Dwarka has helped with ratifying all the neutral hydrogen data. So I think this is a joint effort, and so I want to say thanks before I start.
That's a nice international group there. Very good.
Yes. Okay. So shall I start now, Francis?
Go ahead, fire away.
Okay, so let me start by reminding everyone about the dark matter halos. We know now for several decades that our galaxies are immersed in dark matter halos. And the first real strong evidence for that was by Vera Rubin in the mid-70s, late 70s, who showed that the non-declining rotation curves indicates that there is a lot of unseen matter in the outer disks of galaxies, and theoretical work by Stryker and Peebles also confirmed that. It was very important to have a large dark matter halo for the stability of disks. Now that's been known for a long time now. But we don't know about the details of these dark matter halos. We don't know, for example, a simple thing as where do the dark matter halos end? What's their sizes? And if we don't know their sizes, we can't really tell much about their masses. We don't know their density profiles. We also don't know their spin and their shape.
Right. Yes.
So I think, Francis, there's a lot we don't know about dark matter halos and the nature of dark matter. But if we want to learn more about dark matter, we got to look at galaxies, because that's our environment. So we got to look at galaxies. So keeping this in mind, I was looking and trying to understand the shapes of halos. And before I started, I just looked over the history. Now, if you look at the simulations, because it's well known that galaxies have halos, there have been a lot of simulations in the past, the N-body simulations, which have modeled the galaxy dark matter halo as a spherical solid kind of a body as a potential.
Right, right. Mm-hmm.
Static potential. Then later on in the last, I would say last 10, 15 years, the halos have become live. So they're made of particles.
Oh, good.
And the particles, the halo particles interact with each other. They interact with the disks of the galaxies. So theoretically, the whole ideas about galaxy halos have been changing. I think in the last 10 years, there have been cosmological simulations which have shown that galaxy halos can have a lot of different shapes. Right now, we have the TNG simulations, the EAGER simulations, the Auriga simulations. All of these simulations indicate the galaxy halos can have different shapes and maybe also different spins. So this also was very important background for for developing our understanding about the shapes of halos. And especially if you think about our galaxy, our Milky Way, if you look at all the tidal streams that are coming in, if you look at SMC, LMC, you can use these tidally disrupted satellites to put some kind of bound on the shape of our Milky Way.
I'm with you. Yep.
And it's been and the view has been changing. Sometimes there are some studies which say that it's prolates, some studies which say that it's not. So there can be, from both theory and observations, I think you can have halos which are not only different shape, but inside, internally, their shape may also be changing with radius.
Ooh, yes. Okay.
Now, I just want to mention a couple of, the studies that people have done historically for halo shape before we launch into my own work.
Okay.
So I think the first approach for determining halo shape was from the polar ring galaxies.
Okay.
Okay, so these are disk galaxies with these rings of stars and sometimes gas associated with them. And they are due to the accretion of small satellite galaxies. And taking that to be spherical, the polar ring to be spherical, one can put estimates on the Q, on the axis ratios of the halo.
Okay.
So that's been one approach. But there aren't many galaxies with polar rings. So there have been other methods. For example, if you have a galaxy disk which is flaring at the outer parts.
Okay.
So the gas is like a sandwich here, but the sandwich becomes puffy in the outer parts.
I like that.
So those kind of edge-on galaxies have also been used to kind of estimate what can be the potential or halo potential, or basically the dark matter halo shape.
Cool.
And over here, I've also listed several other things: the flaring of the disks, also the globular cluster system. The globular cluster system, the small clusters in our halo and in other galaxy halos, their distribution using models have been shown to give a kind of an idea of the potential shape of galaxy halos.
I'm with you. Cool.
Yeah, that was really cool. Yeah. So there have been all these other methods. Now, when we started looking at this problem, I realized that one thing that people haven't done is look at neutral hydrogen velocity dispersion, not rotation.
Yeah.
Okay.
Okay.
Now, the reason why I chose velocity dispersion is neutral hydrogen is because neutral hydrogen often extends way out in galaxies.
Yeah.
So it extends way beyond the stellar disk. And in those regions, the halo potential dominates. So if we want to probe the halo, dark matter halo potential, neutral hydrogen is our best probe.
Okay.
Because it's going out into the outer parts.
So
that was one of the reasons why we chose neutral hydrogen.
Thank you. Very good.
And neutral hydrogen velocity was used by Vera Rubin to make the rotation curves.
Yeah.
And it's been used by a lot of other people, edge-on galaxies. But the neutral hydrogen velocity dispersion has never been used to constrain the dark matter halo potential. So this is the first time, and that's why we thought that it was something people should look at.
Absolutely.
So
Very
if
cool.
you want to look at the velocity dispersion, it's good to take a face-on galaxy.
Yes. Yes.
Yeah, so we're looking at a face-on galaxy. And if you look at a face-on galaxy, the neutral hydrogen is actually tracing the vertical z direction velocity dispersion.
Okay.
Okay, so that's why the equation, the first equation, and I'm not going to show many, but the first equation here is the hydrostatic equilibrium equation.
Yes. Yes. Okay.
Yeah. Equation 1.
Mm-hmm.
Okay, so the hydrostatic equilibrium equation is nothing but an equilibrium between the force of gravity, which tries to pinch the disk, and the pressure in the disk, which is fighting gravity. Okay.
Right. Pressure balance.
So
Yep.
in the case of neutral hydrogen disks and also stellar disks, it's the velocity dispersion of the stars and the gas, which is fighting the gravitational force in the vertical direction.
Yes.
So that's why I've got here neutral hydrogen is a probe. So on the left-hand side, there's rho, density of neutral hydrogen. There's the gradient of the neutral hydrogen as a pressure term, dptz. And on the right side is the force, just the force. Now, the force here is composed of everything. It's got the halo, it's got the stars, and it's got the gas as well. Got everything. Okay, so that's why in the equation below, equation 2, you see here the density term for the Poisson's equation, equation 2, it's got stars, gas, and it's got dark matter halo, rho H.
Rho H. Okay, that's our halo. Very good. Okay.
Okay, so now we've got the disk composed of all these three components. And what we had done a work about a couple of years ago, 2020, where we showed using similar results, that there is some dark matter associated with disks. Now what we're doing is we're taking that dark matter, but modeling it with a potential, and that's equation number 3, phi h, simple logarithmic potential.
Yes.
But that logarithmic potential has something interesting. It has a z and it has a q under it. That q is the oblateness of the halo.
Right. So,
okay. So it's the flattening of the
C over A or A over B, depending on what you're doing. Yep.
Okay. Okay. So we're now going to do the maths. I mean, I put that in. You can just skip down a little bit.
Turn the crank. Turn the crank.
We took the exponential profile for the vertical direction, for the stars. Typically these kind of equations are used. So then if you go further down, so equation 5, you can see that we've got an equation where we have the stellar density and we have the velocity h1 dispersion, which is helping to probe it. But it's a very complicated equation, right? So if we want to apply it to some, some real galaxies, better to make it simple. So what we thought is, let's go to the outer parts of galaxies. The outer parts of galaxies, the stars become very less. There's very little stars. So you can drop the stars term. Okay? And if you go very way outside, then the assumption number 6 equation, that really holds. So it's okay.
Okay, I'm with you.
Okay.
Good. I'm with you.
So if you go a little up, you get a simple equation, which is finally equation 7, 8, and I think we'll go straight to equation 9.
9. Okay, boom, boom.
Okay.
Boom.
So,
boom.
So you see, Francis, in equation 9, it's really simple. You just have a couple of unknowns.
Yes.
You've got the unknown V0, which is the rotation velocity in the galaxy. We can get that using the Tully-Fisher relation, as long as we know the mass. Okay. There is the thickness of the H1 disk. We can get that from some empirical observations of edge-on galaxies, ZG0. Okay.
Excellent.
Then there is the unknowns are the velocity dispersion, number one. Okay, that's in
Yes.
the denominator.
Yes.
And the second term is the surface density of neutral hydrogen.
Yes.
Okay.
Right. Okay. That is
So this equation, this is the equation that we started with doing our applying to observations. So this
Okay.
equation 9 is the most important equation.
Okay.
And so if we want to determine the Q factor, the oblateness of halos, what we need is velocity dispersion from the neutral hydrogen maps.
Yes.
And we need the surface density of neutral hydrogen.
Yes.
And all the corrections have been put in, so this is fine.
Cool.
So after this was fixed, then we looked for the face-on galaxies. Okay, that's the sample galaxies and the data. And that was a little bit tough.
I bet. Okay.
That was tough, yeah. Because we didn't want to do new observations because that would take too long, doing a huge survey. We
Right.
wanted to take existing public data. And so we took the data from things, the H1 Nearby Galaxy Survey. We took data from the little things, the H1 Nearby Galaxy Survey.
Hunter, yep.
You know, small galaxies. We also took a couple of galaxies from the VLA Angst data survey. So basically, all our data is using the very large array, the VLA.
Yeah.
It's all, number one, archival data, and number two, it's all using the VLA.
Nice.
And the VLA has produced some really good resolution neutral hydrogen images. So that's why it was very important.
Nice.
And the sample is given below in table 1.
Okay.
So you see the sample, in this sample, you got a variety of galaxies. The first 8 galaxies, starting from NGC 628 to 6946, they're all pretty big galaxies.
Yeah.
They're galaxies. Yeah, they're nearby galaxies, they're based on, they're very well studied. And if you look at the velocity, rotation velocity V0, which is column 1, 2, 3, 4, 6, 7, 8, 9, 10. Yeah.
Yep.
So you see the velocity, rotation velocity, it's been shown by a lot of people that the more massive the stellar component of a galaxy, the more massive stellar galaxies have larger rotation velocities. So that is very evident if you look at the first 8 galaxies here. Yeah. They have large rotation velocities. But then when you come down, then you see the velocity going down. So it's in the 40s and in the 50s. Yeah. And the last 2 galaxies are like small dwarfs. Yeah. So they have rotation velocities of only around less than 30 kilometers per second. Yeah. So this was a good variety to start with. It was a struggle because getting a face-on galaxy is not easy. And so I give this, a lot of credit goes to Roger also for looking up the galaxies.
Yay, Roger. Thank you.
Yeah. Now, I want to just tell you in a couple of 1 or 2 minutes, the procedure for getting the velocity dispersion, which is in this paragraph below. So traditionally, velocity dispersion is the moment 2 maps in neutral hydrogen. The moment 2 maps. Okay. Okay. The moment 1 maps are the velocities. Okay. And moment 2 are the velocity dispersions. Okay. So initially, I did try to use the velocity dispersion, but it gives you a very average value. Okay. So instead, we use a procedure which is now in the last 7-8 years has become very common. What it does is it takes the neutral hydrogen cube, okay, and over the cube, the method fits the velocity dispersion to the different pixels. Okay. So we are getting pixel by pixel neutral hydrogen velocities, fitting it with the Gaussian. Yeah. Okay. So what we did for these galaxies, since they're nearly face on, we did azimuthally, nice rings. We constructed rings, and we found the velocity dispersion, fitted it to the cube, okay, and then we stacked it over each ring.
On each pixel, yeah. Cool.
And so after stacking, the signal to noise became much better. So that was very important. So the velocity dispersion, so the technical know-how about doing this came really from the second author in the paper, Roger, and it's due to him that we got such good signal to noise velocity dispersion. And that's why I think our results are really reliable.
Cool.
We also use the surface density of the neutral hydrogen. Okay. We know that the stellar disk is exponential. It goes down like this.
Right assumption, yes.
Okay. But the neutral hydrogen varies. Sometimes it's actually absent in the nuclear region.
Yeah.
Okay. So we could not assume a form for it. Instead, we actually measured the surface density, solar mass per kiloparsec squared over the disks of the galaxies.
I'm with you. Yep.
So if you go back 1 minute, if you go back to equation, I think equation 9.
Yes.
A little bit up. Yeah, equation 9.
Bandwidth lag. It's all good.
Yeah. So we've got the velocity dispersion from the stacking using the H1 cubes, and we've got the neutral hydrogen surface density. What we don't have here is the stars, and that's because we're doing this estimation in the outer parts of the galaxy.
Yes. I'm with you.
Okay.
Very good.
Okay. So we can move down a bit. Maybe I can just show some of the velocity dispersion plots in the appendix, Francis.
Sure, let's take a look at that. So the dispersions are in the appendix. There we go. H1 velocity dispersion plots. And there we go.
Yeah.
I'll wait till the bandwidth settles a bit, and there you go.
Yeah. So you can see the velocity dispersion seems to be kind of similar for nearly all the galaxies, and that really surprised me. In the centers of galaxies, it's sometimes a bit turbulent, like 4736. In the center, it rises.
Yes, right here.
That could be due to star formation, right? But we want equilibrium.
Yeah. What is the vertical dash line in each plot?
Oh, the dash line is the R25 radius.
Ah, thank you. Okay.
It's the P-man. And so that's approximately a measure of where the optical disk ends, stellar disk.
And
so we did all our calculations outside the R25 line radius.
Okay. I'm with you.
So you can see some of them, actually, one of them I found really amazing, and that is 6946 in the second row.
6946, yes. Let's zoom in on that one a little bit. 6946.
Yeah. So you can see here, 6946, even after the R25 radius, it's still continuing as flat.
It's flat, yeah.
Yeah, it's flat. And that really amazed me. Because in those radii, there is no stars. There's no real stellar disk.
Yes.
So the halo potential must be very important for keeping this disk stable. And so that's why it's very important to, just notice. And when I looked at this, it just reminded me of the flat rotation curves that Vera Rubin made, It's not declining. It should decline, but it's not declining. So that really shows you the importance of the dark matter halo, the outer disks of galaxies, but not just, the rotation curves, but also for the velocity dispersion.
That is kind of curious. You mentioned it, and it's, it's more I look at it once you get beyond R25. It is kind of curious that all the H1 velocity dispersions of, are of order 10.
They do look,
even from these little dwarfs all the way to the big spirals. Yeah. Okay, cool. I'm with you.
Yeah. That was really a very eye-opener. Another thing before we move on is that the velocity dispersion is not much more than 10 kilometers per second for all of them.
Right.
I thought that was pretty interesting.
That's very interesting. Whether you're a big spiral or you're a little dwarf down here at UGC 833. Curious. Very curious. Okay. Nice.
So now we can just go back up and I can just show you the how the plot. Yeah.
You want this one? Yeah, let's do this one.
The galaxies. Maybe we can go. Yeah, we can stop here for a minute. So this is the plot of the oblateness. So the halo flattening versus radius for our 20 galaxies. And so this is really our result. And what is surprising is that it varies. The top two rows here are the massive galaxies, the top two rows.
Right.
And the bottom rows are the small dwarf galaxies.
The little ones.
Yeah.
Yeah.
And you can see here that the oblateness of the larger galaxies is around, it lies around between 1.5 maximum.
Yes.
Yeah. But if you look at the little galaxies, the oblateness, if you look at the axis, it can go as small as like 0.1 or 0.2.
Wow.
That is really amazing.
Really.
Yeah, like a little sausage.
Yeah, really elongated.
Yeah. So that was really amazing. Now, then, people have asked questions about this because one of the reasons why we are getting such flat halos may be because we have assumed that the ratio between the disk height and the disk radius and the height of the disk is constant. Okay, RD by ZD.
Okay, and that's a constant.
We have assumed that.
Yeah, right.
Because it was shown using many studies. Yeah.
Okay.
But it may not be. You could have some galaxies where the H1 disk is flaring.
Yes, and then it won't.
A little bit flaring. If that happens, then if you look at the equation, you'll see that the Q should increase.
Yes.
Okay.
Yes.
Okay. So that's one disadvantage of our results. Okay. But we'll be correcting that soon. We're now doing a study for the disk thickness of neutral hydrogen. Yeah.
Okay.
So now that I presented these results, I think I'll go to implications. Okay. Yeah. So these two plots, the plot figure 2 on the left and figure 3 on the right, these are, like, I would say, our major results.
Okay.
What we've shown on the left-hand plot is a plot of the stellar mass versus the Q factor, the oblateness factor.
Right. Okay.
And you can see, Francis, that there is a kind of a trend.
Yes.
It's not strong, but there is a trend. And when we calculate the correlation coefficient, it's close to 0.8, 0.78.
Okay.
So it's not bad. But there is a lot of error bar. There is some. So that's why I didn't fit it with the curve. It's not something we can.
No, I wouldn't do that. Yeah.
Yeah. We can't do an empirical relation yet.
Right.
Q versus stellar mass without more galaxies and without reducing the error.
Right.
Right. But it does show that the more massive galaxies, the more massive galaxies are having higher Q values on average.
And a Q of 1 means a sphere?
Yeah.
Right. So
Q of 1 is a sphere and Q of, say, 2 is prolate.
Yes.
Okay. Like a spindle. The Q of 0.5 or 0.4 is flat.
Yes.
Wash.
I'm with you.
Oblique.
Yes.
Okay. So as we're going closer to 0, we're getting more oblate. Yeah, these are all oblate.
Yeah. These are a little more spherical.
And these are a little bit, but it's a mixed bag.
Right.
For the massive galaxies, it's a mix. Some of them are oblate, prolate.
Right. Yep. Some one. Okay.
Yeah.
And it's 25. Okay. And then on the figure 3.
On the right, this is what I found really interesting. Plot figure 3 on the right.
Okay.
So if you plot the gas ratio with the gas ratio, which means the mass of neutral hydrogen plus molecular hydrogen divided by the total baryon mass.
Okay.
And the baryon mass is made up of stellar mass,
Right.
molecular hydrogen, neutral hydrogen.
Uh-huh.
Okay.
Uh-huh.
Okay. So on the x-axis, I plotted this. Okay, M baryon, gas divided by M baryon. And on the y-axis, we've got again the oblateness.
Wow. Huh.
Okay. Now, if you look at it, the first thing you see is that all the gas-rich galaxies, the ones which are on the x-axis to the extreme right, yeah?
Yes.
Okay. On the extreme right, all these galaxies have more gas than they have stars in mass.
Yeah. They're
all oblate.
quite active.
Okay.
It's compressed. It's a disk. Yes. Okay.
Yeah. So it means that all of our dwarf galaxies, which are often gas-rich,
Right.
are going to be flat.
Okay. Okay.
But you look at the stellar-dominated galaxies, where the gas to baryon mass ratio is much less than 0.5,
Yes.
which means the mass of stars is larger than the mass of gas.
Mm-hmm. Mm-hmm.
Okay.
We're going to.
So for those galaxies, it's a mixed bag. Okay. It can vary. It can vary from even 1.2 all the way down to 0.2.
Right.
Okay. So it can vary from there to there. It could be quite a big range. So I think this really was, I felt, the major result. It showed that the gas-rich dwarf galaxies have a low oblateness, which could be due to higher spin, whereas the stellar-dominated galaxies can have a variety of Q values. This, I think, was our major result. And so then the next question is, why does this happen? What are the implications for this result?
Yes.
And so that's what we felt that there were like basically 2 points.
Okay.
Okay. The first point explaining figure 3 was that, the dwarf galaxies, they have a larger spin. Okay, so we have two main implications for our result. We've got, basically our results are showing that the smaller gas-rich dwarf galaxies have more oblate halos, so they've got flatter halos.
Mm-hmm.
And whereas the massive galaxies have a mixture of Q parameters, so they can be flat, a little prolate, they can have various values.
Okay.
So one of the explanations for this could be that the small dwarf galaxies, they have halos which are spinning faster. And if you just think of this in very layman terms, when you have something that's spinning faster, then it becomes often flatter.
Pizza dough.
Huh? Pizza dough. Right. Okay, that's a good analogy. So if you have the dwarf galaxies spinning faster, which is also shown in the cosmological simulations, then their Q will be lower. So the halo spin could be just one reason. Cool. Now, why would the massive galaxies have a variety of halo spin? Now, that could be because of the tidal torques in the early universe. Okay. So the tidal torques, which, there's a whole tidal torque theory by Jim Peebles, which states that galaxies passing by one another will give each other a kick, a little tidal torque. Right. And that can be very strong for the small galaxies, but it may not affect the large galaxies, which may undergo mergers and have a variety of halo shapes. Cool. And then the second thing could be that the more massive galaxies, they have, they're the ones which more massive stellar disks, they could be having orbits which are more radial. And this has been shown in simulations, that when you have more stellar-dominated systems, then you have more radial orbits. Actually, you would think the opposite, because there's something called adiabatic contraction. The gravity of, the stellar disk might pinch the halo towards it. But that doesn't happen here, mainly because of the orbits of the particles in the dark matter halo.
Right. Cool.
Okay.
Very nice.
And the dark matter spin, which I forgot to mention, it's like a potter's wheel, okay? So if the halo is spinning fast, then it makes the disk spread.
Yeah, right. Very
Okay,
cool.
so that's why we get in the dwarf galaxies, which are spinning faster, halos are spinning faster, we get more, low density disks, flatter halos. So it all kinds of ties in,
Yeah,
not just with what we think, but also with simulations, what we're seeing in some cases, like in Gaia, I think right now our halo appears to be kind of spherical. And if you go back to our plot, one of our plots, where you have stellar mass versus the halo oblateness, then our galaxy's mass, stellar mass, is of the order of a few times 10 to the power 11, or close to around 10 to the power 11.
Yeah.
And it lies in the ballpark. All of these galaxies lie in the ballpark of around Q is equals to 1.
Yeah, very cool.
So things tie in, can be better, of course. Always they can be better, but they do appear to be kind of
it's hanging together. It's hanging together self-consistently. So very cool. Very nice. Mousumi, I want to thank you so much for walking us through your very lovely APJ letter. Thanks. And
you're welcome.
Oops, we had a little bandwidth lag there.
Oh, okay.
All good.
Okay.
So you mentioned it a couple of times, and so let me push on it a little bit. Where do you think we go over, let's say, the next 2 to 5 years? Are there additional yet more catalogs one could go through? Would one consider doing a survey to get more face on galaxies? Is there additional theoretical work that could be done? Just sort of where do we go over the next couple of years on this fascinating topic?
So I think the first thing we want to do is we want to get the thickness of galaxy H1 neutral hydrogen disk, because the thickness, H1 disk thickness, is a very important parameter in our model.
Right.
So that's the next step that we are planning. Roger and me are planning to look at edge on galaxies, and we get the disk thickness.
Nice.
Then apart from that, we'll of course look for more face on galaxies. And there's the SKA coming up, the square kilometer array. And we are hoping that will really give this work a push. Definitely. Because with good SKA data, we will get a much better idea of the halo shapes.
Yeah.
And apart from that, on the theoretical side, I'm doing simulations with my students because I do simulations and observations. So we're doing some simulations or looking at, simulation data products of cosmological simulations to understand more about halo shapes.
Very cool. Well, I really look forward to seeing this topic evolve over the next couple of years. It'll be very exciting. Very nice.
Thank you. Thank you.
And thank you once again, Mousumi, for walking us through your APJ letter.
Thank you very much for waking up so early. Thanks.
All good. And I hope this made everyone's astronomy day just a little bit better, and we will see you on the next one. Bye-bye.
Bye.